This is a 60 FPS E-Ink monitor at 300 ppi. E-Ink isn't known for speed, but this one refreshes 60 times per second. It took 4 years to build, 20 plus PCB revisions, and getting it to refresh at 60 Hz was probably the easiest part. This is how it started. I was building an E-Ink laptop, and I faced a problem. Every system-on-a-chip that supported E-Ink back then was designed for e-readers. Low power, slow processors, limited interfaces. I can't build a laptop with that. So I needed to decouple the system-on-a-chip from the screen. I would put an FPGA-based driver chip between them, essentially building my own E-Ink controller. I wasn't even thinking about high frame rates. In fact, the laptop design had a bar-type LCD, kind of like a large touch bar. Because I assumed I would need a fast display for some tasks, the E-Ink would be slow, and that was fine. While designing this controller, I had an idea of how 60 FPS might work on E-Ink. It wasn't the main goal. I just needed something that's reasonable for an E-Ink screen. If 60 FPS worked, great. If not, 15 FPS would be fine. I built it. Tried the idea. And it actually worked. So how does this work? And why hasn't anyone done this before? Traditional E-Ink controllers use a global update timer. When you need to refresh the screen, you wait for the previous update to finish. The update takes about 100 milliseconds. So worst case, your new image waits 100 milliseconds before it's even processed. You can make this timer tick faster so you get higher frame rate. But the E-Ink is slow. If it ticks too fast, the image becomes washed out. The particles just don't have enough time to respond. So what you get is a trade-off between refresh rate and the contrast ratio. Some controllers try to mitigate this with multiple regions, maybe 4 to 16 regions that can update independently. But this requires the software to manually manage these regions, and you are still limited. My approach was different. Treat every single pixel as its own update region. When something changes, that pixel immediately starts updating. No waiting. The result? You get both high frame rates and high contrast. The old trade-off between the speed and quality just disappears. The downside? Memory bandwidth. When using this 13-inch panel, displaying monochrome image, traditional controllers need just 20 megabytes per second. Mine needs 540. That means DDR3 instead of basic SD-RAM, DisplayPort instead of USB. It's expensive, and for reading books, completely unnecessary. But for a monitor, it changes everything. At that point, the project changed. Before I could worry about the laptop, I needed to build a really good monitor first. Over the next couple years, I worked on this in my spare time. Starting with the display itself, E-Ink can't do non-flashing grayscale, period. So dithering becomes essential. I implemented 3 algorithms: Bayer dithering, blue noise, and error diffusion. Bayer is fast, but shows visual patterns. Blue noise looks better. Error diffusion gives the best quality, but it's hard to scale to high resolutions. Dithering works, but it just doesn't beat the true grayscale. Well, except for flashing. Existing monitors either implement the slow flashing mode or skip grayscale entirely. What I built is a hybrid. When the image changes, switch to fast binary mode. When it has been stable for a while, re-render in grayscale. It works well for reading, less so for everything else. But that's fine. Building my own controller means I can optimize for my use case instead of being stuck with preset modes. Hardware needed work as well. The first prototype used a full-size DisplayPort. I later switched to USB Type-C with DisplayPort out mode. I also had to switch from an integrated power management IC to discrete DC-DC converters when the PMIC was discontinued. To protect the screen from unexpected latch-up events, I added full voltage and current monitoring. Every change meant at least a new PCB revision. Each revision taught me something new. Then I got the first case design back from a contractor. That was the first time it looked like a real product, not just a bare PCB on my desk. It felt real. I started showing it at conferences, Hackaday SuperCon, Latch Up, Cross Supply's Teardown event. People were genuinely excited. They wanted this to exist. Everything was lining up. The technology worked, people wanted it, I had the designs. I just needed to give it one final push. So I quit my job. The plan was straightforward. A few focused months to finish this thing. Polish the design, get it manufactured, ship it. I thought I was prepared, at least I thought. Right after I went full-time, Eink announced new panels, higher resolution, better specs, and cheaper. This should have been great news. Except, I had to redesign everything for the new panel. Higher resolution requires me to use a higher bandwidth decoder IC, higher bandwidth DDR memory, new FPGA to be able to support these, higher current power supply. Added up, that's almost everything I have on the board. At very least, half a year delay. Then came a bigger redesign. Before, I designed the board first, then built a case around it. For the final product, I flipped it. Designed the form factor first, the chassis, the exact dimensions, the mounting points, then make the board fit. The entire design is much more optimized and coherent, but more time spent and another major revision. Then, I got a fully assembled prototype. I showed it at Design Shenzhen. I felt so close again. But the prototype was unstable, too unstable to ship. Random glitches, video would drop out. Sometimes it just wouldn't initialize. I needed support from the supplier of the video decoder chip. We had an NDA. We had a service agreement. They refused to help. They wouldn't even provide the driver code to begin with. I had to pay extra under the table just to get the source code to use their own chip. And the code didn't work. They wanted more money for working code. Their sales kept trying to upsell me to more expensive chips that I don't need. Months went by. Thousands of dollars wasted. The product still didn't work. Eventually, I switched to a different vendor. Luckily, much better to work with. But their chip wasn't available when I started, so even if I had known better, there's nothing I could have done. I kept grinding. I added touchscreen support. That meant integrating a new touch controller, writing drivers, handling collaboration. I had proper flicker-free front light implementation. I had a frame rate limiter, because lower frame rate can still be useful for clarity. I added a low power mode that saves power when not plugged in, and an on-screen display to control all these features. Each feature sounds simple in one sentence. Each took weeks to implement properly. And the finish line kept moving. So really, I had 90% done. I just have 90% left. Here's what full-time on this project looks like. I work more hours than I ever did at my job. Nights, weekends, the boundaries blur. I play fewer games. I have less free time. I solve problems I never wanted to learn about. And here's the thing. I don't regret it, because it's mine. When I make a decision, it happens. When I solve a problem, it stays solved. When I want to implement a feature, I don't need to convince anyone. I'm tired. but it's my tired. It's not always easy. It's not always fun. Profitable? We will see. But fulfilling? Yes. And fulfilling doesn't always mean fun. 4 years after the first prototype, it's real. 13.3 inches, up to 60 FPS, extremely low latency. Multiple display modes. Because I control the logarithm, I can optimize for real use cases. Touchscreen, front light, color option. And it's open source. The hardware designs, the FPGA gateway, the firmware, all available, because that's what it was always supposed to be. This is what I have after 4 years. I'm still learning. This is just the start. Thank you for waiting for this video. I know it has been years since I released the demo video. If you want to support this project, it's live on CrowdSupply. Links in the description. If you want to build your own, all the designs are open source. And if you just want to see what an open source high refresh rate E-Ink monitor looks like, you just did.